Now, in this video, I want us to look at what they call first order. First order, look at first order. Remember, we are still on the is first order exact DEs. First order exact DEs. I want to simplify for you this such that you don't ever cram it again. What do we mean by first order exact DEs? Now, imagine if you have, they have told you to differentiate x, y, something like this. This is an implicit function that we differentiate using product rule. They tell us that keep x constant, differentiate y, you get dy by dx, and then keep y constant, differentiate x, you get 1. So therefore, the derivative of xy with respect to x turned out to be x dy by dx and then plus y. Now, in DE, this is where it is interesting. This is called exact DE. Why exact? Because we can trace where it came from. We can trace where it came from. That's why from first order exact DE is where we get those that we call linear that need integrating factor. Yeah, I'm going to also explain why that is that. Now, this one is called an exact DE, meaning whenever I know where the exact that DE came from, exactly minus changing anything, it means that is an exact DE. Yeah. So we can use another example before we go to calculating those exact DE. We can say you were told to say to differentiate something like x square y dy by dx. So you keep x square constant, you differentiate y, you get dy by dx plus, remember use product rule. Keeping y constant, differentiating x, you get 2x. Now we have something like the derivative of x square y dy by dx is equal to x square dy by dx plus 2xy. Now, if you find something like x square dy by dx and then plus 2xy equal to 5, and then they tell you to solve a DE. This DE, this one, we call it exact. Exact DE. Why exact? Because it can be exactly retraced where it came from. Without adding anything, we can trace it where it came from. Exactly. Now ask me, how do we identify that this one is exact, this one is not exact? How do we see it? How do we see it? That is when we go to our example. How do we see that this one is an exact, this one is not exact? Let us see. Example 1. Example uh, example 1. So for example, you are given example 1 and then you are told to solve, yeah, solve the DE. Yeah, DE stands for differential equation. So solve a DE. Now you are given a DE like this. You are given a DE like this. You have part A. Let me write 3. We solve 3. So you have something like y square plus 2xy and then dy by dx is equal to 1 out of x square. Now you have something like this. We want to know whether this is exact. We are going to do 3 such that we get a clear picture. So we want to know whether this is exact DE. Now, how do you identify exact DE? You identify exact DE but by how a derivative was done. Now, you should always concentrate so much. If I try to change some color here, you should always concentrate so much on where the dy by dx is. Now, in this dy by dx, it means something was kept constant and another one was differentiated. So in this case, when you find dy by dx, it means y was differentiated but x was kept constant. If that is true, so you come and say, I'm going to obtain where they came from with respect to x. Now, in this first one, this one that we are talking about, x was kept constant, but y was differentiated. So what was kept constant here is what? Is x. So x was kept constant. Now, what was kept constant in this one? What was kept constant here was the one that was differentiated here. And what was differentiated here is the one that was left as a constant here. Now, when you know that in this case x was left constant here, was not differentiated. So it means here x is the one that was differentiated but y wasn't. So therefore, we end up having our y square, just like that, is equal to 1 out of x square. So when we go further, we realize that we can have our xy square dx is equal to 1 out of x square. So you can go ahead to integrate. Now, this is where we keenly see. If you want to test, if you differentiate this, if you differentiate that, you must exactly get that expression. Exactly. That's why we call it exact. So if we go ahead to integrate on both sides, integrate with respect to x, integrate with respect to x, realize that we shall have our xy square is equal to this is negative x to power negative 1 and then plus sc. So therefore I have xy square is equal to 1 negative out of x and then plus sc, as simple as this. Now I want to do another example such that you confirm the knowledge how to get that, how to get uh, this, how to get that, how to get the exact function where it came from. So this one is that. To make the worker clean, let us first be like removing some such that the work is a bit clean. So example 2, B, part B, part B, part B, part B. I want to have something like, let us write something like ln y and then plus x out of y, and then we have dy by dx is equal to sec x, then tan x. Now, here I want you to see that in this first expression, automatically x was differentiated. That's why here it was kept constant and we are seeing it. Now, in this one, ln y, here in ln y was differentiated. That's why you have a dy by dx. So if after knowing that one, it is simply meaning that that expression came from having x ln y. As simple as that, with respect to x. Because when you keep ln y constant and differentiate x, you'll get 1 from that expression. So you'll have ln y there. When you differentiate x, you get 1, so you stay with ln y. And then when you go to this one, when you differentiate ln y, you get 1 out of y. But remember, x was kept constant, so attach dy by dx. As simple as that. So is equal to, you have sec x tan x. So this is when you go ahead and integrate. So you go ahead and integrate on both sides. So the logic is always to defeat how to get the exact. And then when you integrate, math is so simple, so easy things. So you have x ln y is equal to, now you battle now the integral when you integrate the other side. So when you integrate this side, so sec x tan x dx. Now, for you to know what the integral of sec x tan x, we use what we call change of variables. Change of variable. So we are going to let change of variable. We know it very well that we let one that removes the other. So we let, this case, when we let u to be something that you want, but in this case, if you look at, when you let tan x, when you differentiate tan x, you get sec square x. Sec square x cannot eliminate everything. So the best choice is to let u equal to sec x. When you differentiate u with respect to x, you get sec x tan x. We are there. So making dx the subject, you have du out of sec x tan x. Putting it back, we have defeated the number. You have x ln y is equal to integral of sec x tan x times du. We didn't want to put this one directly back because you see they are going to cancel. Over sec x tan x. So this goes with that. So we end up having x ln y is equal to integral of du, which will be x ln y is equal to u plus s. But what was our u? Our u is sec x. So x ln y is equal to sec x plus s. As simple as that. As simple as that, you have defeated. Lastly, such that you confirm the knowledge. Lastly, let us drop one that may be as if complicated but so cheap. C, imagine you are given something like, let me try to write the one that may be assumed to be complex, but it is so cheap work. So imagine you have xy square, this one is okay, plus plus c x square y plus x square y plus x square y, then dy by dx is equal to sec square 2x. sec square 2x. Now this one you have to be careful, very careful, very careful. Now, to know where this one came from, if you look at here in this first one, in that first one, x was differentiated. In the second one, it was a square. So meaning, when they differentiated x here, it was something like a 2, it was something like a 2xy square. Now, when they differentiated y here, it was something like a 2x square y dy by dx. So they were 2. But where did that 2 go? Where did that 2 go? And how do you retain it? To retain it, you multiply throughout by 2, such that when you multiply throughout by 2, you have not changed anything. Nothing has changed. So when you multiply throughout by 2, you have a 2x y square plus 2x square y dy by dx is equal to 2 sec square 2x. So you have not changed anything. However, you are doing math. So this one can be known where it came from now. It came from x square y square with respect to x is equal to, now we are having 2 sec square 2x. So we do the integration. So when we integrate on both sides with respect to x, we shall have x square y is equal to, now when you integrate a sec square, you'll have 2 out of 2 tan of x plus a c. So you can use all methods of integration that you know. So this one went with this. So we end up having x square y square, we had forgotten it, x square y square is equal to tan x plus a c. As simple as that. Yours. Question. I want to give you yours. Solve the DE. Yeah. I want you to go slowly with the video, pause it where you have to first copy or understand, and then you continue. So yours, solve, I'm giving you 2. 2 says you have 1 minus 2x e of y dy by dx, and then minus 2e of x is equal to sec square x b. Yours b is b is 2 t e of x, and then plus t square e of x d let me say dx dt is equal to sine of t plus t cos of t. So drop your answer on my WhatsApp. Drop your answer on my WhatsApp. My WhatsApp is, drop your answer on my WhatsApp. If you need any help, still use that WhatsApp. So that is my WhatsApp. Don't forget to subscribe if you haven't subscribed. share it with your friend such that you can understand together, such that you can understand well together. So here we have looked at what exactly is R. So that's our main focus for this. What was the exact DE? Don't forget to subscribe if you haven't subscribed. Like the video. We meet in the next